Hello everyone, welcome to my presentation on attention-based dynamic graph learning framework for asset pricing. I am Ajimuddin and this work is quoted by Jinwan Tao and Dantung Yu, and we all from New Jersey Institute of Technology. Before going to get into details about our works, let's have a brief overview of what I'm going to talk today. First, I'm going to discuss about equity market networks, its attributes and complexity associated with modeling equity market networks. How we try to resolve this problem using our three-stage digraph model and its framework. To validate our model, we also perform extensive analysis, so I'm going to discuss the analysis and the associated result, and finally I'm going to discuss the major contribution of our works. So let's talk about equity market networks. Firms in the equity market are not standalone entities, they are connected. They are connected by supply chain networks, sector similarity, ownership structure, and return structure. These networks play an important role in firms' return. If you look closely, stocks price barely move alone. They often move in cluster, either in same or opposite direction. And this is also a prime notion behind portfolio theory. An impact of one firm can affect the whole economy. For example, we see in the 2007 financial crisis how Lehman Brothers bankruptcy have a cascading effect in the whole market. But the problem is when we want to model these networks, the network is not static, it's dynamic. Two firms whose prices move in the same direction in January can move exactly opposite direction in December. For example, as you can see from this figure in between AEM and Walmart, in the earlier stage they have some correlation, but in the middle years from 2016 to 2018 they have a very good positive relation, and in the final few years they have again very small correlations. And another final problem is this network is unknown. We cannot say this like unlike social networks or root networks, financial networks is not given. So people use different techniques to identify these networks. For example, in 2018 Journal of Finance paper, Herskovich used sector similarity. But the problem with sector similarity is that sector similarity cannot identify dynamic nature of the network. For example, two firms like let's say Apple and Google, they're in the tech industry and they might remain the tech industry for the foreseeable future, right? Another problem is having the same sector doesn't guarantee similar return. For example, if we go back to our earlier example, AMD and Apple both are in tech sector, but their return is not same. Historically, people use and most dominantly use Pearson correlations, but the use of Pearson correlation normally result a both positive and negative coefficient. But the network techniques mainly developed in CS or IS are mainly from like positive graph. So in order to avoid the complexity, finance people normally ignore the negative edges. But the problem is we cannot just ignore negative edges. They bear significant information. They're the basic of portfolio theory in finance. And also you can see from this graph, this negative information also provide information about clustering or sector similarity. And in different time period, if we look at this the structure of negative edges, we can also see how or what's going in the whole market. For example, you can see in December we have both positive and negative correlation net edges. In April, the beginning of COVID-19, almost all negative edges disappear. Again in December, negative edges start to appear, and it's give us information about these sectors. Like this group of firms is completely different from this group of firms. So we ask ourselves, what should be an ideal model? An ideal model should capture time-varying information from the network. An ideal model should able to capture nonlinear connectivity and dependency. Not only the information we are given, but also they can capture information from the data. They should incorporate the time series pattern. Like we know that the price of tomorrow's price of a stocks is dependent on today's price, and in finance theory people develop a huge literature just how to identify this momentum and momentum reversal. So our network, our effective or ideal model should build on some recurrent framework like GRE or LSTM. And finally, it should be appropriate for finance application. Like it should be able to deal with dynamic relation, it should be able to deal with positive and negative relation. So we try to incorporate all this attribute into our model. First, we use an attention mechanism to learn the dynamic network structure in the US equity market. We also use mask attention to incorporate both positive and negative relationship among firms. And finally, we use a recurrent diffusion convolution neural network to model the spatial and temporal dependency among firms. The recurrent networks in model the temporal dependency, and diffusion convolution model the spatial dependency among firms. So how we define our problem in these settings? If we look at the finance literature, like pure finance literature, normally we can group the theory that used to develop, used for predicting future return can be grouped into two categories. One based on historical return, where people assume that tomorrow's price is a function of yesterday's and some historical time periods, and they use normally RMA or some those kind of model. And this model actually based on momentum and momentum reversal, all this theory are based on this, comes from this assumption. The second group actually comes from factor models, where we assume that tomorrow's price will be a function of a company's microeconomic market or security specific characteristics. From a French 5-factor model, Carhart liquidity, these are mainly go into this factor model. So we try to combine these two in our graph learning based prediction frameworks. So we actually try to learn our graph from historical return, and then from this historical learned graph, we use this learned graph plus the firm characteristic to predict future return. So how is our dynamic graph learning framework look like? Our dynamic graph learning framework is actually use 3 layers. First one is actually, of course, as I'm saying, we have 2 input, historical return and firm fundamental or characteristics. We use 3 layers. First layer is actually embedding layer, where we actually try to reduce the dimensionality of the return data. So return data can be either like 10 days, 1 week, 1 month, 2 months, or 2 years. So normally if it's using like we are using 1 week or 1 month data, we probably do not have to reduce dimensionality. But when we are using in like 2 years or like larger and larger data points, then we have to reduce the dimensionality, because unlike other models, like other common techniques, we are not learning one graph, we are learning an individual graph in each time point. So in order to reduce the computational complexity, we try to learn embedding layer using a singular value decomposition on this return data. In the graph learning layer, we use attention function to learn the edge coefficient between each of these firms. And in diffusion convolution layer, we are actually using the learned graph to perform a recurrent diffusion on the firm characteristics. We actually use 2 GRU layer. In the first layer, we perform recurrent diffusion on these firms characteristic. In the second layer, we actually concatenated output of first layer and output of our hidden embedding layer and perform another convolution diffusion. This actually allows us to actually incorporate return information again into our model, because in the first analysis we are only using return to learn graph, but we also want to use return for the prediction model too. So this bypass actually allows us to do this. So of course, as I was saying, SBD on the historical return allow us to reduce dimensionality. We are using only fast L principal components, where L is of course lower than K, or number of firms. In finance, literature suggested only 3 or 4 principal component is enough to capture almost 100% of variance in especially financial time series. But we still use in our cases is more than on 10 or greater than 10 L. In the graph learning layer, we use actually attention mechanism in like 2014 Danus paper. He actually shows us how attention is only attention is enough to learn any type of relation in with neural networks. So we use this attention function to identify the interdependency between each farm and its neighbors. We use actually a softmax function to actually introduce nonlinearity, and because of this, our edges become the edges actually come into a range between 0 and 1. Although in literature it is suggested that a simple attention strategy, attending all node pairs, ignoring the structural information, can achieve desired objective. But in our case, remember, we also try to reduce computational complexity because we are learning a huge number of graphs. We use actually masked attention. So we use actually two masked attention, one from positive network and one from negative networks. And this also actually allow us to improve the performance because not all farmers connect to each other. So we actually help our model to in this phase. We actually use Pearson correlation, which is actually widely used as a measure of correlation in the farm networks with Pearson correlation, and we use a threshold function to specify these networks. And finally, we actually use two positive mask where correlation is greater than 1 and negative mask where correlation is less than 1. So after this softmax function and mask operation, we end up with two affinity matrix, one for positive networks and one from negative networks. In the third layer, we are using recurrent diffusion convolution layer. Recurrent diffusion convolution has root in physics, and it is extensively used in recent graph literature to identify the information diffusion process in the networks. Normally, the information diffusion process is identified using a random walk in networks, where the random walk on graph G can be defined as a strange transition matrix A and a random walk normalization matrix or diagonal degree matrix D. In our case, we use two diffusion, one for positive networks and one from negative networks. And here S is the number of steps in the random walks. And after this two diffusion, we actually concatenate information from the both this diffusion at the end. So because of this two diffusion, our output from the diffusion layer is actually a tensor with dimension n times q times t. In order to model the recurrent informations of the time series data, we actually use a GRU. And what we did, we actually replaced the GRU gates with graph diffusions. And finally, we actually predict our output with a simple dense layer where we use our output of our two-layer GRU with multi-layer perceptron. So let's talk about some experiment. We use two sets of data, one from monthly data and one from daily data. Monthly data are coming from S&P 500 monthly data are coming from Russell 3000 index, and we have 1098 from. Daily data are coming from S&P 500 index, we have 441 from. We use some filtering procedure to come up with this number of farms, and we also use 21 monthly farm characteristics and 24 daily feature as farm characteristics. In order to compare our model, we select baseline from two different literature. We use three traditional finance model, Fama-French five-factor model, probably the most widely used asset pricing model, multivariate regression using all our fundamentals, and ARIMA. We use also 5 machine learning based model. First one is empirical asset pricing by machine learning. It is a recent finance paper published in Review of Financial Studies, and of course we use compare LSTM, compare our model with NBITS, and of course we use attention functions, so our model has some connection with graph attention. We compare with this paper, and we also, of course, because of the convolution recurrent, we also use the diffusion convolution neural networks as a benchmark model. Result. We first analyze our model on model performance on forecasting future return with the performance metrics RMC, MAIN, MNP, MAP, and we found that in almost all almost all metrics, our model performed really well compared to those benchmarks. For example, in FF5, our model performed 9% better than FF5 in monthly data and 12% better than EAP MLP. We also seen that compared to machine learning based time series model like FFLSTM, FCLSTM, our model about to perform 10% better compared to DCRN. We are able to perform 6% better. The performance improvement is also robust for daily data. If we try to see why our model performed better, we actually able to realize that our model actually able to harness the advantage of both graph attention mechanism and DCCRN, because we actually use both attention and recurrent convolution into our models, so they can easily outperform this more individual model of this individual models. Second, we try to see our portfolio performance of our model. First, we try to build a long shot portfolio based on model predictions, and you can see this about this time period, our model actually able to perform 1.5% monthly return on portfolio with a very relatively low risk 3%, and compared to other model, our model Sharpe ratio is also very low. And in other models, we also see that EAP MLP and NBIRS also perform well. And if you see this graphs, you can see that our model is also not immune to market downside. So when market is performing bad, almost all models perform bad, and our model also perform bad. But one thing is, we can assure that our model is actually able to recover very fast. So if you see after the COVID crisis, almost all model like the market drops, like share price of every company drops, so there is no way to make money. But our model actually able to identify companies which can actually perform better in the middle or later part of the 2020, especially after the COVID, like for example Amazon or Walmart, and you can see our model perform really well. You also see that EAP MLP also perform really well at the later period of that time. One of the most intriguing feature of our model is actually graph learning capacity. We try to see how our learn graph value and market relation, and you can see in different economic event, our learn network is different. You can see after when in the initial COVID pandemic, almost all negative edges disappear. Brexit don't have any impact on our networks. During elections, most negative edges disappear, but we still have negative edges. And December 30 is a normal graph. We have both positive and normal condition. We have both positive and negative networks. We also see that the number of positive edges or negative edges in the network is also associated with market impact, especially in crisis situation. Almost positive, we see a high spikes in positive networks like Eurozone crisis, Brexit, or COVID-19. To summarize, our works actually offer a novel solution to two critical problems in asset pricing literature: the interaction among firms and the evaluation of the interaction. We develop a flexible attention mechanism to learn new networks from the scratch or improve upon initial networks. And we also, in our paper, we show that firm interaction is bidirectional and related to the market analysis, and we cannot just ignore negative networks. And incorporating this network information can allow us to improve stock return prediction. And through our analysis, we showed that our proposed model outperformed many traditional asset pricing model. Even it also outperformed advanced machine learning models. Just a caveat that we find that in our model still not immune from the market downturn. So if we are using our model for actually trading, we should be considerate. Thank you everyone for attending my discussion. Have a good night.